In the previous videos, we saw how to prepare sequential data, how to structure our sequence-to-sequence models, and we had our first glimpse of recurrent neural networks. And the problem we ran into was that recurrent neural networks had potentially unbounded memory, but practically tended to forget things quite quickly. In this video, we'll look at the LSTM model, which is a model that doesn't have such a strong forgetting property. And the structure we'll follow in our explanations is taken from this blog post by Chris Olah, which is also part of the required reading. The problem that LSTM solves is the problem of long-term dependence, a problem we encounter a lot in language processing. So a sentence like this: I was born in France, etc., etc. When I moved to Amsterdam, so I'm fluent in. If we want to predict what the next word in this sentence will be, most language models will tell us that it's not aquarium, because that doesn't fit any of the general theme or even the grammar of this sentence. But a network with a poor long-term memory will most likely fit the recent word Amsterdam to the language Dutch and predict that Dutch is a likely next word. Whereas a model with a long-term memory will realize that given the entire structure of the sentence, it's more likely that French is the next word, at least in theory. So in short, what we want is a model that is able to remember things that happened far back in the sequence. The problem is that in order to remember far back, you need to aggressively forget. All of these words in between the word France and the words fluent in need to be forgotten in order for the word France to remain active in memory. So the key to remembering is forgetting. Which brings us to the LSTM. The LSTM, which stands for long short-term memory, is a recurrent neural network that has active mechanisms for forgetting and remembering, controlled by learnable gates. This was quite possibly the first deep neural network in history, with convolutional neural networks as a close second in 1998. The basic structure of an LSTM looks like this, where the orange blocks are cells, which we'll look into later. And for each time step, one of these cells is computed based on the input, produces an output y, and passes to the next cell two values: a copy of the output that it's just produced and a cell state C. So let's look at what happens inside of this cell. It's a bit complicated at first sight. These are the formulas that are evaluated within the cell. Now, these are not complicated formulas. From left to right, on the left, we are producing a vector x prime, which is simply the concatenation of the current input and the previous output. This x prime is fed through a number of one-layer feed-forward networks to produce four intermediate values f, I, c, bar, and o. And then these values are combined by purely linear computation, purely linear element-wise computation, into two values ct and yt. And these are the values that are passed as output and to the next cell. However, it may not be quite immediately obvious why this would be such a successful way of doing things. So I'll try and illustrate that visually using the following notation, part of which we introduced already in the previous video. So when two lines join, we will take that as a concatenation of the two vectors represented by those two lines. When a line is accompanied by a boldface letter, we will take that as a feed-forward network, so a multiplication by a weight matrix and by an addition by an accompanying bias vector, which is not indicated. The sigmoid activation, we use this familiar symbol. The tan H activation, which remember is just a sigmoid activation, except it ranges between -1 and 1. We use the same symbol but in purple. And for element-wise operations like addition and multiplication, we'll use a circle. Using this notation, the inside of an LSTM cell looks like this. So we'll walk through the basics of what's happening here step by step. And the main thing to focus on is this line here at the top, which has been termed also the conveyor belt, which is basically the line by which the previous cell state passes to become the next cell state. So we get the cell state of the previous cell, ct minus 1. It is multiplied by a vector ft. A second vector it times c bar t is added to it. and then it's passed on to the next cell. Now the main thing to note here is that these are all purely linear operations. There are no activations here, so we get perfect non-vanishing gradients across the conveyor belt. And if we zoom out to all these cells in a row and draw the conveyor belt over all these cells, we can see that all the way back down history, these cell states are all operated on only by linear operations. And this is why in LSTMs we get such a nice non-vanishing gradient all the way back down history. So what are these values, ft, it, and c bar t, that act to manipulate the conveyor belt? Let's start with ft. First, as we saw before in the formula slide, we create a value x prime, which is the concatenation of the previous output of the network and the current input, and that is fed to a sigmoid activated feed-forward layer to become ft. And the main point of this sigmoid activation here is that we get a vector of values between 0 and 1. So what this does is if the activations are very low, then the activations, the values in the conveyor belt, are lowered as a result, because we're multiplying by a value close to 0. Which is why this is called the forget gate, because this value has essentially the power to reduce the activations of the conveyor belt to make room for new things to remember. So basically this forget gate is telling us for certain elements in the vector, make some room in our memory because there's new important stuff coming up. While in other parts of the vector, it can set the activation very high, close to 1, which means keep the values in the conveyor belt for those elements as they are, because for those elements we want to remember what we had in our memory. So that's what the forget gate does. It tells us, looking at the input, how much we need to reduce the activations in order to make space to remember new things. Once we've made space, we need to design the addition that we're going to make to the conveyor belt. And that's done by this gate mechanism, which takes again this x prime and feeds it in parallel to a sigmoid activated and a 10H activated feed forward layer, giving us respectively the vector it and the vector c bar t. So c bar t we can interpret as the value that we want to add to the conveyor belt. And because this is 10H activated, we are limiting the extent to which we can add values to the conveyor belt. So we can add the values that we like, but they have to be between -1 and +1. And we can interpret this it as a kind of way of controlling which elements of this vector are actually going to be added as a multiplier on top of this c bar. So again here, if the values are close to 1, then all the values, then all the activation of c bar is going to be added to the conveyor belt, and if they're very close to 0, then the values will be scaled back so that whatever was originally on the conveyor belt is retained. These two values are multiplied and then added to the conveyor belt. So it's interesting to lift this out and see what's happening here, lift this out of the LSTM cell. This basic principle of taking an input, multiplying each by a separate weight matrix, one sigmoid activated and one 10H activated, and then element-wise multiplying the results. This is known as a gate. And you can think of this in the computation graph on the left as computing a value on the right that you'd like to add and computing a mask on the left that controls how strongly those values influence the final result, and then element-wise multiplying them into a result vector. It's a gate mechanism, and after the LSTM became popular, it popped up in lots of different models as well. So you might see it separate from the LSTM layer. Moving on to the final part, now that we've done to the conveyor belt what we wanted to do to the conveyor belt, all we need to do is produce the output. And here again we have a gate structure, where one half of the gate structure, the 10H activated part, is actually the value that we now have on the conveyor belt. And we multiply that by a sigmoid mask produced by the weight matrix WO, which tells us which parts of the conveyor belt value we actually want to output. So these values are element-wise multiplied and fed into the output of the neural network and into the next cell. And that's the whole LSTM neural network. So to show you why the LSTM is such a big deal, I've taken some examples from a blog post called The Unreasonable Effectiveness of Recurrent Neural Networks by Andrej Karpathy, where he explains most of the things I've explained in this and the previous video. And he finishes up by some autoregressive modeling examples using an LSTM. So we saw this in the first lecture already. Autoregressive modeling is where we take sequences of natural language and we feed the sequence as input, and we set the sequence shifted one step to the left as the target output, so that the model learns to predict the next character in the sequence. And because the model is a causal model, we know that it cannot look to the future to simply look what the next character in the sequence is going to be. It has to infer it from the characters in the past. And once a model like this is trained, and once it's successfully trained, we can do autoregressive sampling on it, by which we mean we start with a small seed of characters, we feed that to the neural network, we look at the last character of the output sequence, where the neural network produces a probability distribution on all possible characters. We sample that character, we add that to the seed, and then we feed the whole thing through the neural network again, and we loop that to sample character after character after character. And the result obviously depends on what bag of natural language we train on. So here are a few examples. Starting with Shakespeare. That's about 4 megabytes of text, I think. So enough to train on. And it gives us this result. So this very Shakespearean looking language is entirely generated by a neural network that was purely trained on a character level representation of Shakespeare with no extra information. So we see very natural looking, Shakespearean looking language with broadly the kind of meter you'd expect, with very Shakespearean looking character names. What we should say, what you will see if you generate a long stretch of text, is that there is no long-term consistency in the text. Locally, it all looks very convincing, but especially with something like Shakespeare, you will not see the same character name recurring over and over again. The neural network simply at each point generates a new character name. So for a long term, it's still not convincing, but locally, it looks very good. And remember, this is character level language modeling. So it has actually learned that there is a word think, that there is a word shall, and that there is a word approached. For a slightly more challenging problem, we can look to Wikipedia text. So we take 100 megabytes of Wikipedia data, and we let the network generate text. And what we see is that not only do we get, again, locally convincing natural language, we also get wiki markup. If you've ever edited a Wikipedia article, you know that to make a link, you add these double square brackets around a phrase. So here the phrase John Clare is a link to another article, except of course that the name John Clare is probably hallucinated by the network. But note that the Wikipedia syntax is entirely valid, all the brackets are closed, and more importantly and more impressively, the things within the brackets are actually the parts of a sentence that you would link to a different article. And what you see is that the neural network even occasionally hallucinates a link to a different website, like here at the bottom, where there is a Yahoo link that doesn't actually exist. There's no page if you copy paste this into your browser address bar, but it does look like a valid URL. So that's what the neural network has learned, what URLs look like. And because Wikipedia pages occasionally contain little snippets of structured information in the form of XML, the network will occasionally go into XML generation mode. And finally, probably most impressively, the LaTeX example. So the authors fed a large corpus of LaTeX code to the neural network and had it generate some LaTeX code, and with a few minor corrections managed to actually get it to render like this, which I'm sure if you've ever tried to write any LaTeX, you'll understand how impressive that is, because it's something that even human beings struggle with most of the time. So that's the amazing power of the LSTM network. To finish up, let's look at a few variants that you might encounter in the literature. The first is an LSTM with peephole connections. A peephole connection is basically a connection from the conveyor belt to different parts of the network. So in the traditional LSTM, we only add to the conveyor belt, and in an LSTM with peephole connections, we allow the conveyor belt also to influence the rest of the network as an input. And the simplest way to do that is to simply concatenate it in this early concatenation where we create x prime. We simply add it to the concatenation so that x prime is now a concatenation of 3 vectors, the previous output yt minus 1, the current input xt, and the current value of the conveyor belt ct. A more radically different version of the LSTM is the GRU, the gated recurrent unit, which looks like this. Its main purpose is to keep the power of the LSTM, but to simplify its structure. So what we see here is that there's only one value passed between cells. We still have a conveyor belt. We still have only linear processing. But that conveyor belt is also the cell's output. This means that there's no output gate and the output is not activated because the output needs to be linear. We simply output the value on the conveyor belt. And the second thing to note is that when we compute the current value of the conveyor belts, if we look at this last value yt here, we're basically taking a linear interpolation between the previous value on the conveyor belt and the current value suggested by the cell, y bar t, and we're linearly interpolating between these two values using the value zt. So we take 1 minus zt multiplied by the previous value and add that to the current suggested value. Practically, there's no evidence to suggest that the GRU is strictly more powerful or strictly better at certain tasks than the LSTM, but it is a little bit simpler. And finally, the convLSTM, which is a good variant if we have a sequence not of vectors, but of high-dimensional data, high-dimensional structured data. For instance, if we're analyzing video, then we might get a sequence of video frames or a sequence of images stored as image tensors. Now we could, of course, flatten these into vectors, but then our weight matrices in these fully connected layers in the LSTM would get very, very big. So to avoid that, what we can do is replace every fully connected sigmoid activated operation in the LSTM with a convolution instead. So these 4 formulas in the LSTM layer, we simply replace the linear operations with convolutions. So the W's are now convolution kernels, and the X's now represent image 3 tensors. And throughout the LSTM, all these image tensors stay image tensors, and they are convolved, and the rest of the LSTM is simply element-wise operations as before. And this is a very powerful and efficient way to analyze video footage. So, what have we learned? We've looked at LSTMs, which stands for long short-term memory. They were invented in 1997 by Hulkreiter and Schmidhuber. They were probably the very first effective, really deep neural network. They operate by maintaining a linear conveyor belt over time, which keeps the gradient strong as they're propagated back down the network. And these are manipulated by short-term nonlinear operations. And through these nonlinear operations, the gradient may vanish, but these are always short-term with connections only to the current input. These are probably one of the most successful models of the past 2 decades. They're now competing for the limelight with self-attention and transformers, but they are by no means irrelevant yet. And there are many variants around, like Peephole LSTMs or GRUs, but most of them perform broadly the same. And the key features to that performance seem to be this linear conveyor belt that allows the gradients to look far back in time, and these gates built up from a combination of sigmoid activated feed-forward layers and 10H activated feed-forward layers. In the next video, David will explain how we can use convolutions to build networks that are competitive with LSTMs.